Hey, hello everybody. Good to see you. Glad to see such a great uh, audience here for our student speaker today. We let us wait just a few minutes, about 2 more minutes. Some people are still coming on, okay? And before I introduce Sunday Aween and uh, his mentor, Dr. Wu, we'll just wait a couple minutes, okay? Mhm.
Hello, Dr.
Hey there. Yeah, we're just waiting a few minutes, Nelly, to get a couple more people. Uh, hey,
Yeah, let's see. Is this meeting being recorded? Yeah, they're recording it. Okay, we'll wait for a few minutes. Okay.
mhm. Yeah, just a few minutes here.
Okay.
Another minute. Mhm. Okay. Yeah, let's go ahead and begin then. Okay. Looks like we have a very good turnout. Very pleased. So thank you again for joining us in this series, our faculty student seminar series, Pathways to Artificial Intelligence, Machine Learning, and Data Science. This series is occurring every Monday where we're presenting faculty and student results, basically, as they've been using artificial intelligence and machine learning. Today, we have one of our students, our computer science students. I'm going to ask the his mentor, Dr. Jinwei Liu, to introduce him. Dr. Jinwei Liu is assistant professor in the Computer Information Science Department. Jinwei, you want to go ahead and introduce your student?
Um, yeah. Um, Good afternoon, everyone. My name is Jingwei Liu. Currently, I'm assistant professor in the Department of Computer and Information Sciences. And my student is Sandy Alvin. And so today, currently he is my graduate student, a master student, and his research interests include um, resource allocation and resource scheduling in cloud computing and clusters. And he has completed some research papers. He had he had two publications. Today he is going to present his first publication research work, and also he has another paper which has been accepted. Yeah. Um, thank you.
Good afternoon, everyone. Uh, can you hear me?
Yes.
Okay. Yeah. My name is Sandy Awini. I'm from Ghana. I'm in computer science department. Like my mentor just said, my research interest is in cloud computing, cybersecurity, machine learning, and then AI. This is one of our papers. Um, that I worked with Dr. Liu during last semester. And then it was accepted as a poster. And then we presented it in Houston at a DT4HS conference. That is Digital Twin for Health Society. So the topic, before I start, I would like to thank Dr. Anlo and then his team for this privilege. Thank you so much. So these are the authors of this poster. Sandy Awini, Dr. Liu, Dr. Anlo, Dr. Parabatista, and then Dr. Tiran Suarez. The topic we worked on adaptive scheduling of digital twin workloads using topology-aware reinforcement learning in high-performance computing. Okay, so this is the route map, the presentation route map. We have introduction, system model, proposed approach, performance evaluation, ablation, and then discussing, conclusion, and then the reference. So this is the introductory part. We know that digital twin are no longer just concepts, but they require critical for this thing, smart grid manufacturing and then climate modeling, which are also required for continuous loop of real-time data to maintain synchronized virtual replicas, which are used in modeling and monitoring complex cyber physical systems. Digital twin applications kept on increasing. So there's a need for high performance computing to be able to execute the workload. So there's a need to meet the stringent latency and then throughput requirements. But our traditional schedulers are poorly suited for the dynamic workloads. Traditional systems are batch oriented. They are not dynamic. They are not able to adapt to dynamic workloads. And so due to this, these are the current limitation of our traditional schedulers, which are just static batch oriented jobs. And when as digital twin pipeline data increases, and then communication becomes intensive. Now, here we model digital twin workflow as directed acyclic graphs, where we have the vertex representing the computational task with compute and then CPU demands. And then the edges represents the data dependency and data volume requirements. This is how we visualize our workflow. Here we have the digital twin workflow modeled as directed acyclic graph. We have tasks here. As you can see, task 1, task 2, task 3, task 4, and task 5. And these tasks are assigned to this topology-aware scheduler based on readiness. of predecessor's task, whether transfer data has been completed or not. And that is what is making it to be the topology aware. And so they are now organized into nodes, which are in racks, as you can see, rack 1 and rack 2. This is where the nodes or the task are being processed and then measured as an outcome based on max span, total communication, and utilization. And so here we used smaller workloads. First, we use small workloads, and when we use the small workloads, we were able to get some improvements. And then we use larger ones. When we use the larger one, there was also an improvement. And so we went further to remove the topology awareness nature of this particular scheduler. And so when we remove the topology awareness nature of it, we categorize the performance into topology aware and then no topology aware, which is still being adaptive, because this whole system is the adaptive, is our method, adaptive, which is the topology aware. So when we remove the topology awareness nature of it, we realize that the one with the topology aware has higher performance as compared to the one without topology awareness. So when I say topology awareness, it means tasks are being scheduled based on predecessors task, the size of the workloads, and then without the topology awareness is like the other scheduler, FIFO, the greedy scheduler. Those ones, they don't they don't consider the readiness of the jobs in queue. They don't consider the time of the time of completion and other ones to execute. So because of that, the no topology aware was not good as compared to the topology aware. So like I said earlier, the execution completion for the topology aware depends on the completion of all predecessors tasks, completion of required data transfer, and availability of assigned compute nodes. So here, before anything execute, which is our method, the adaptive style topology awareness scheduler, before any task execute here, these are some of the factors the task will have to go through, or the workload will have to go through before being executed. And so the first one is completion of to make sure that the predecessors this in task are completed before anything can come in, and to make sure that completion of the required data transfer are this thing completed, and then the availability of the assigned node for it to be able to execute. And in our method, we compare it with two baselines, which is which are the traditional schedulers, uh, the heuristic greedy scheduler, and then the FIFO, which is first in, first out scheduler. We compare our adaptive scheduler with those schedulers. So this explains our model. You know, the simulated high performance computing clusters. They are organized across racks. The nodes. The nodes here are organized across racks. We have rack 2 and then rack 3. The model also incorporates rack level locality and bandwidth asymmetry. Communication delays occur for tasks placed on uh, different nodes and racks. So our model extends the hierarchical multi-agent reinforcement learning to HPC scheduling domain. This hierarchical multi-agent reinforcement learning, that was the previous paper, the first paper I worked with Dr. Liu during the summer. Basically, we have global controller and then the local agents. And for the global controller, they control the high level cluster scheduling strategies. And then the local agent manage specific node level execution decisions. So our policy was based on proximal policy optimization. And then it operates over a structured action space of candidate nodes implemented as a lightweight deterministic decision rule, which allows our system to be able to re-evaluate data without the need to train anything online. And this the brain of our model, the reward function, which is the coefficient of throughput times the throughput itself minus coefficient of latency times latency minus coefficient of resources cost or utilization cost um, times minus the coefficient of communication delay penalty times the communication delay penalty. So this formula regulates performance and efficiency trade-offs. So we use this formula to measure the latency and then the throughput against resources cost, which is the resource utilization, and then the penalty for the total communications delay. So the policy, this is what the policy observes. I mean our policy, the proximal the proximal policy optimal. Observe task dependency readiness and estimated run times, node availability and rack locality, current communication load. So this is what it observes before it measures. It brings out the measured output as based on the FIFO scheduler, and then the FIFO scheduler, our adaptive reinforcement learning scheduler, and then the heuristic greedy scheduler. So this is our experimental. We set up an 8-node simulated high-performance computing cluster with the rack-aware topology, and then the synthetic workflow. And here, that's the DAX. Those are the size of the task. So ranging from 10 to 60 tasks. And we also average every 10 over 20 random seeds for reliability. So these are the metrics we measured against the sizes against, the dark size, the max span, that's the completion time of the final task in the workflow, and then the communication time. So we measured dark size against the max span, and the max span is the completion time of the final task in the workflow. We also measure dark size against communication time, or the total communication time, which is the cumulative data transfer time between tasks. We also measure the dark size, the same dark size against utilization. And utilization here is a fraction of the available compute capacity used. So this is for small to medium workflows. The dark size we use 10 at first, and then second one 20, and then the last one for the small workflows. Realize that here our adaptive reinforcement learning style under normal circumstances, max span is supposed to decrease, but when you compare our method with the FIFO Robin scheduler, round robin scheduler, our method performs far better than that, and also is within the greedy earliest finished scheduler, very competitive to that one, um, for the max span. And then the utilization, the resource utilization, under normal circumstances, the resource utilization is supposed to increase. And so when you look at our method, the adaptive reinforcement learning style, throughout the resources utilization, it increased, making our method an outstanding one when it comes to resource utilization. And then when you look at the communication time, which is supposed to decrease, um, our method compared to the FIFO round robin performs very well as compared to the FIFO round robin, and stays within the greedy earliest finished. And so our adaptive reinforcement learning achieve higher utilization than the standard FIFO, and even the greedy earliest finished scheduler. And performance remain competitive within the 5% of the greedy, for the max span is within 5%. As compared to the grid, our method is within 5% for max span, compared to the greedy earliest finished. And then our adaptive reinforcement learning achieves the higher utilization throughout the FIFO method, and even compared to the greedy earliest finished. We move to a large workflows. So we increase the dark size to 40, and then 60. So when we increase that, our method reduced the max span by approximately 29% relative to the FIFO. And then the total communication overhead reduced by approximately 47 compared to the FIFO. And then our method, which is the adaptive reinforcement learning style, consistently achieve the highest cluster utilization for even large data size, or large dark size. And you realize that at the task 60, our method reduced the max span approximately 29% as compared to the FIFO. So we visualize the mark span distance, the mark span performance against that is against the dark size. So here realize that the FIFO round robin scheduler he keep on increasing, which is supposed to decrease as the data size increases, but it keeps on increasing, making it not the best scheduler for digital twin workloads, because digital twin workload keeps on increasing. So as the workload becomes larger, the FIFO round robin will not be able to that scheduler will not be able to adapt to it. And when you look at our our style stays within the greedy earliest finished. Though here the greedier the greedy earliest finished perform better as compared to our style, but our style also remain competitive within the greedier earliest finished scheduler. And also our style is adaptive. It's an adaptive style, or our scheduler is an adaptive scheduler, which means it will be able to adapt to any workload size or any dark size. Here, this is the communication overhead. That's the total communication time. We measure the dark size against the total communication time, and here our style, our scheduler. You realize that our scheduler remains slightly constant, uh, not increasing as compared to the FIFO round robin scheduler. And so as the dark size increases, you realize that the greedy earliest finished also increases rapidly as compared to our style. So that means if we had increased our dark size or number of tasks to, let's say, up to 100 or more than that, then our style will definitely outperform the greedy earliest finished scheduler. So here our method or our style reduces communication overhead by up to 47% compared to the FIFO. And for the cluster utilization or the resource utilization, we also measure it against the dark size, the same dark size. So here, our scheduler, and under normal circumstances, cluster utilization is supposed to increase as the dark size or the number of tasks increases. So our scheduler maintain an increase in the resource utilization or cluster utilization as compared to the other two schedulers, which are traditional schedulers, and they are static and batch oriented. They cannot adapt to when the dark size increases. So that means because they are not adaptive, they are not able to perform well as compared to our scheduler. And so you realize that our scheduler consistently achieves the highest utilization across all workflow sizes. And so to further investigate or to further confirm that our method is good, or topology awareness is good in our method, we performed an ablation study. And then with the ablation study, we removed the topology awareness nature of it, but it's it's still being this thing adaptive, though our is still being adaptive, but remove the factors, those topology awareness, for instance, like the readiness of the task, the to for it to ensure that maybe like the predecessors tasks have been are completed, and then data require, or there is availability of assigned compute node. So we remove all those factors and then that one measure the one without topology aware against the topology aware. So when we did that, and the purpose is to isolate performance gains from network locality, to show that topology aware is really necessary when it comes to scheduling workloads in digital twin. And so we did that, and here for the max span, at the data size we used 20, 40, and 60. So for the max span here, which is supposed to decrease, the topology aware adaptive style or scheduler uh, maintains better max span as compared to the no topology aware. And then the utilization also, which is supposed to increase. The first one increased, but the other two did not increase like that as compared to the first one. And our communication time here, which is supposed to decrease, our method outperformed, or the topology awareness nature of our method or our model outperformed the no topology awareness nature of it. So removing topology awareness nature increases communication overhead by up to 53% for small DAGs directed acyclic graphs size. And for 60 task workflow, communication overhead rises by approximately 34 without topology awareness. And performance gains arise directly from exploiting data locality and network structure. This our related. We also view some other papers. One of them talked about the traditional algorithm, which they used it to try to minimize the max span on heterogeneous resources, like the heft algorithm, the heft algorithm. They try to use it to minimize max span on heterogeneous resources. And there's also another paper we reviewed on that talks about static method failed to adapt to real-time digital twin variability. And these are other papers which focus on real-time task scheduling and freshness ratio. And other also propose proactive allocation for edge devices and offloading. Conclusion. So our proposed adaptive topology-aware scheduler for high-performance computing digital twin successfully reduced communication and improves cluster utilization and achieve the competitive maximum scaling for communication intensive tasks. This where future work may focus on evaluating the responsiveness of the model under workload stages and node failures. Also, they might also focus on trying to assess the stability and recovery time, and try to integrate it with live Kubernetes-based resource managers. Thank you. The research was supported by the U.S. National Science Foundation grant. That's a grant number, and then Florida Agricultural and Mechanical University Title III grant, a Cyber Policy Institute Institute at Florida A&M University. Thank you. These are the reference. Yeah, if there's any question for me.
Sandy, yeah, thank you for your presentation. Yeah, just now I find that you try to explain the experiment results. So one thing I want to I want to provide some comments. Yeah, there are some methods like FIFO, and that is first in, first first out schedule, and also the adaptive schedule and the grid-based scheduler. So sometimes for FIFO, definitely the performance of FIFO is worse than that of the other two schedulers. For sometimes although the performance of the greedy the greedy based scheduler is better than the proposed adaptive scheduler, the scalability of the greedy based scheduler is is not very good. So in that case, the proposed adaptive scheduler has better scalability than that of the grid-based scheduler. Okay.
Thank you.
You're welcome. Yeah, and also for this work, in this stage, the paper has been accepted as a poster paper, but we also received an invitation for submitting of a full paper, and we will try to extend it and submit a full paper to a journal. Yeah, thank you.
Well, congratulations, Dr. Rowena and Dr. Liu, for your enthusiastic research. Please keep going and keep up the good job. Let's open the floor for questions from the audience and hear from them. This is really very specialized research on in your area. So can you, if there is nobody else right now, maybe what let's say, what kind of data can you process with this? What kind of results do you expect to obtain? Now, speak like you're talking to, people who don't understand anything about that, like me. So tell me what can you do, for example, with some chemistry data with with your approach?
Okay. Yeah,
Or
so
any other kind of research data. Cyber physical, okay.
your question again, can you?
All right. Yeah, here it says that modeling and monitoring complex cyber physical systems.
Yeah.
Okay, what is this?
Yeah, so that is the digital twin workloads. You can use it to model and then monitor cyber like physical systems, and that is critical for like real-time data because there's a need to maintain the synchronized virtual replicas. Do
I'm
you
sorry, I'm on
understand?
mute. Smart grids manufacturing and climate modeling. So you can actually model climate
Yes,
changes.
you can
Yeah.
model climate with it.
Okay. What else can be modeled with this approach, using this approach? Any other phenomena, or can this be applicable for something else?
So I'd like to give some additional comments. Actually, for this work focusing on the scheduling of digital twin workloads, and the digital twin can be used in different areas or fields, like healthcare and also um, um, environmental engineering and so on. So um, I mean, for a system like a cyber system, it will generate some workloads or data, and we designed the adaptive scheduler which can be used to efficiently schedule those workloads so that it can eventually um it can help the um, improve the performance of the digital twin system.
Okay.
Yes.
Well,
Mhm.
thank you. I hope that we'll have a chance to discuss this in the future again, and and congratulations for the acceptance of your paper, of course. So well, if there are no other questions, I want to thank Mr. Awin and Dr. Liu for their great presentation and their awesome research that they have done. And I hope to see you all next time. Okay.
Thank you.
All right. Okay. Thank you, guys. Have a nice day, everybody. Okay.
Thank
Thank
you.
you.
Okay. Bye bye.